Hello and welcome back to this video for part 2 of the 2022 Scholarship Physics paper. So for this part, we're going to be looking at questions 3 and question 4. And for the last part, we looked at questions 1 and 2. I'll drop a link below to questions 1 and 2 if you would like to look at that at the moment. So we'll get straight into it. So we'll look at question 3, magnetic slider. So a metal roller of mass m slides without friction down parallel conducting rails of negligible electrical resistance. The rails are separated by a distance L and are connected to each other at the bottom by a resistance R, forming a closed rectangular conducting loop within the rails and the roller. The plane of the rails make an angle theta with the horizontal, and a uniform vertical magnetic field B exists throughout the region. As the metal roller slides down the rails through the magnetic field, it reaches a constant velocity of V. And we want to show that the constant velocity achieved by the roller through the magnetic field is given by the relationship shown below. Okay, so for this question, there's going to be some component of the wave force acting down the ramp, and that's going to be setting the bar down towards the bottom of the ramp. There's also, when the bar starts to cut the magnetic field, there's going to be some perpendicular component that cuts the magnetic field, and that's going to produce a force that's going to be in the opposite direction of, there's going to be a component of the force in the opposite direction of the bar rolling downwards, and it's going to counteract the wave force going down. And once the bar has reached a certain speed, it's cutting the magnetic field at some rate, so there's going to be some rate of change of flux, and that some rate of change of flux is going to induce some force acting in the opposite direction that's going to be equal to that of the gravity force acting down, and the overall F net will be 0, and that will be where the constant velocity has been reached. So for this question, F net equals to 0 at constant velocity, implying that F down equals to F up. To get an expression for F down, we'll look at the gravity force acting downwards. So in this case, we'll have the bar, which we'll use as a point here, having a wave force of mg downwards. And this will be the component down the ramp. We'll call it Fr. And there's going to be some component here added to make the overall force mg. So in this case, we know that this force Fr is parallel to the ramp. So we know that if we were to draw a triangle here, then therefore we know that this angle here is theta, so therefore this angle here is 90 minus theta, so that angle there is 90 minus theta, so therefore, that angle is also theta, that angle is theta, my bad, apologies. So the angle is theta, so this means this angle here, that angle there is 90 minus theta, and therefore by triangles, this angle here is theta. So this angle here, we know is theta. So therefore we say that sine theta is equal to Fr, which is F down the ramp over mg. So Fr is equal to mg sine theta. So that'll be the forces acting down the ramp. In terms of the forces acting opposing the force, we want to find the component of the velocity that cuts the magnetic field perpendicular. So we want to find the perpendicular component of the velocity that is cutting the magnetic field. So in this case, we know that the bar here is going to have some components down the ramp. So we'll call this component some component V. And it's going to be some component, we'll call it VH, that is going to be cutting the magnetic field perpendicular to the magnetic field. And in terms of similar angles, we can use alternate angles on parallel lines to deduce that angle is theta. So therefore, we can say that cos of theta equals to VH over the V, which is the velocity down the ramp. So therefore, VH equals to V cosine of theta. And likewise, we know that F equals to BIL. And in this case, it's going to be the force is going to counteract that of the bar, in terms of the bar cutting the magnetic field in the perpendicular direction. So therefore, the force is going to be acting in the opposite direction, which is also perpendicular. So in this case, it's going to be some F that's going to be acting in the opposite direction. So F, oppose. And again, if you want to find a component acting up the ramp, we simply use triangles again. So we should get F equals to BIL times cosine of theta. Okay, and then this will induce some sort of EMF throughout the circuit. So we know that V equals to IR. And we know there's some resistance on the circuit, which will be given by this resistance R. So therefore, we know that I equals to V over R. So therefore, Vf equals to B V over R times L cosine of theta. And running out of space, but okay, so V times V over R times L cosine of theta. And we know that V equals to BVL, where V is the component of velocity that is cutting the magnetic field in a perpendicular direction. So that will be the VH component, not V. So V here will be equal to VH, the perpendicular component. So in this case, V equals to BVL cosine of theta. And we can actually substitute that into our equation. So we have F equals to B multiplied by V, which is BVL cos of theta, multiplied by L cos theta. Sorry, the space here is... They don't really give enough space, do they, for these scholarship papers, but it is what it is. Okay, so we have F equals to B times BVL cos of theta times L cos of theta over R. So F equals to B squared times L squared times cos squared theta times L, not L, times V divided by R. And we know that we want to equate F down equals to F up. So F down equals F up. I'm just going to borrow some space from part 2. So F down equals to F up. So therefore mg sine theta equals to B squared L squared B squared L squared cos squared theta times V over R. Okay, so therefore we're just going to move everything to the left hand side here. So mg r times of sine theta divided by B squared L squared cos squared of theta. And sine theta over cos theta is tan theta. So this is mgr tan theta over B squared L squared cosine theta. And that is as required. Okay, so that would be our answer here. And you'll get 2 red ticks if you can get that answer there. So just going to free up our part 2 again for the question 2. So explain what difference, if any, it makes to the constant velocity of the magnetic fields in the opposite direction. And the fact is that the force induced only depends on the rate of change of magnetic flux. So when the bar is rolling down in the magnetic field, it's going to cut, there's going to be a perpendicular component of the velocity to the magnetic field that's going to be cutting the magnetic field, and therefore that's going to be inducing a rate of change of flux, and that's going to be causing an induced EMF in the circuit, and there's going to be some back force that's going to be opposing that motion. And if the magnetic field's in the opposite direction, there's going to also be an increase in magnetic flux, and but instead, in this case, the current will be in the opposite direction, so it will be a 180-degree change in the current. And likewise, there's a 180-degree change in the direction of the magnetic field. So these two changes, they'll cancel each other out, so therefore the force that is acting on the bar is still going to be in the opposite direction, which is going to be up against the motion. So there's going to be a component of the force acting against the bar going down the ramp. So therefore there's actually no difference in the overall motion. So therefore the equation still holds. And that's assuming that all of the other, all the magnetic field strength stays the same. So if everything stays the same and only the direction changes, then we expect the force to be the exact same. And you can actually reason this using a little bit of let's just say trying to say some let's try to think of it using okay, so for example, if you think that there's going to be a change in the direction of force to be in the same direction as the bar, this means that the bar will be speeding up. There'll be a component of the force gravity acting downwards, and there's going to be a component due to the force, which is also apparently acting in the same direction, which will speed the bar up. And there's actually nothing, if the magnetic field goes on forever, there's actually no way to slow down. The bar will not be slowing down, which doesn't really make sense. So the bar just keeps speeding up and speeding up. So in this case, if you think about it logistically, that doesn't really make much sense. So in terms of the force, it's always in the opposite direction of the change. So the flux induced will always try to oppose the change. And in this case, opposing the change means trying to reduce the speed or the acceleration of the bar down the ramp. And again, it will reach some constant velocity, which we just shown was given by the equation that we derived above. So we just say there's no difference. No difference. In this case, force acts in the same direction. Same direction. So change in magnetic flux acts against the change. So change in flux opposes the change. So reduce. So it's against the motion of the bar. We can just say that B changes by 180. So B change 180 degrees. I by 180 degrees. Overall, no change in the direction of the force. Overall no change in the direction of the force. So no change in the direction of the force, therefore equation still stands. Yeah, and that's all we need for this question. A pretty short one, just one tick for this one. Question B. An experiment is set up with B equals to 2 Tesla, L equals to 0.5 meters, M equals to 5 times 10 to the power negative 3 kilograms, and R equals to 10 ohms. Determine the accuracy of equation 2 compared with equation 1 at theta equals to 25 degrees. So I think these questions are pretty simple. So it's just really just quantitative comparison of the two equations. So we'll just substitute those numbers into equation 1 and equation 2 and compare the differences. So for equation 1, we'll say that V equals to mgr tan theta over B squared L squared cos of theta. So V equals 2. So in this case, we just chug in our numbers. So 5 times 10 to the power negative 3 times 9.81 tan of 25 degrees divided by B squared, which is 2 squared times 0.5 squared times cosine of 25 degrees. And that equals to 0.252 meters per second. For equation 2, we'll just substitute those parameters in again. So we have 5 times 10 to the negative 3 times 9.81 times 9.81 times there's also a times the resistance, so times 10 there, forgot about that one, so times 10 here, and times of, so divided by B squared, so 2 squared times 0.5 squared, and we're going to multiply by theta plus 5 theta squared over 6, so it'll be 0.346 plus 5 times of 0.346 cubed divided by 6. And this will be equal to 0.248 meters per second. And the difference here will be, if you want to write it as a proportion of each other, so the difference would be 0.252 minus 0.248 divided by 0.252, which is approximately 1.6% difference. Yeah, that's really all we need to do for this question. So it's in my opinion, it's a pretty straightforward question here. And in fact, you actually get 2 marks for this question here. So pretty straightforward here. Yeah, okay. So by calculating the velocity at a high angle of theta equals to 85 degrees, explain if this equipment would be suitable for testing whether equation 1 is accurate at high angles of theta. So for this question, we'll just calculate the velocity. So start off with calculating the velocity and see where that takes us. So we say V equals to mgr tan theta over B squared L squared cos theta is equals to 5 times 10 to the negative 3 times 9.81 times 10 times tangent of 85 degrees over 2 squared times 0.5 squared times cosine of 85 degrees. And this is equal to 64.3 meters per second. Oops, okay, sorry, meters. Okay, so immediately, like, this should be a pretty, like, raising a red flag, because 64.3 meters per second, that's a pretty big speed. And there's going to be a very big distance. You'll need a very strong magnetic field. So 2 Tesla is a very strong magnetic field strength. So you'll need a pretty big distance required within that magnetic field to test reaching this constant speed. So we'll just say that this is a very high speed. This is very... Will take a large time to reach constant speed, so large distance required. Large distance in strong 2 Tesla magnetic field. Hence it would be hard to test, so not very suitable. So hence experiments not very suitable. Okay, so this is not very suitable. So because of the high constant speed that's reached, might require a large distance and using a very large magnetic field as well, which might not be very practical. So definitely not very suitable there. So that's a 2-mark question there as well. Explain whether equation 1 remains valid if the roller rolls rather than slides down the slope. So for this question, it's basically the first thing when you're seeing if the roller rolls is that some of the energy is being converted into rotational kinetic energy rather than linear kinetic energy. So in this case, there's going to be some component of energy that's going to be going towards the rotational kinetic energy, and some will be converted into linear kinetic energy. However, whether or not the energy is converted into the rotational kinetic energy or linear kinetic energy, it still holds that the forces acting on the rod are exactly the same at constant speed. So at constant speed, the forces acting on the rod are exactly the same. So there'll be the gravity force down the slope, and also the opposing force up on the ramp. It's going to be the same forces. So therefore, the maximum linear constant speed reached will be the same. The only change that will be happening here is that since some of the energy is indeed being converted into rotational kinetic energy, the roller might have to roll a longer distance in order to reach that constant velocity. However, at the end of the day, that constant velocity will still be the same as described in the formula, since the forces acting on that rod are the same at constant speed. So the F net is still 0, and it's exactly the same forces, the force acting down the ramp due to gravity, and the force acting up ramp due to the opposing force due to the change of flux as the roller cuts the magnetic field. So there's no effect in this case of equation 1, so no effect on equation 1. No effect on equation 1 since forces acting on the roller are the same. So same Fg down ramp and same F up due to opposition force at the constant speed. We can say that some energy is converted into a rotational kinetic energy. So some energy is converted into EK rotational, or rather than linear. So therefore, it might take longer for the constant speed to be reached. So it might take longer time to reach constant speed, but the value of that speed is the same, but the velocity is the same. And that's all we need to say for that question. So that's again just a 1-mark question there. Okay, let's look at question 4, orbital dynamics. So we're given some data there. The James Webb Space Telescope, JWST, has a mass of 6.16 times 10 to the 3 kilograms. It was launched on Christmas Day in 2021. It is now orbiting at a point called the L2 Lagrange point, where it will remain in a direct line with the Sun and the Earth, as shown on the right. State the period of the orbital of the JWST around the Sun. Okay, so a big giveaway for this question, it just says that the Sun and the Earth is just going to be remaining on one line. So it's just always going to be in line with the Earth. And if it's always in line with the Earth, this indicates that the angular velocity of the Earth and the telescope is exactly the same. So therefore, it's going to take exactly the same amount of time to orbit the Sun of the telescope as does the Earth. So simply, this is a very, very straightforward question. It's simply just going to be exactly equal to that orbital duration of the Earth around the Sun, which is 365, not 62. What am I doing? Okay, 365.25 days. Come on, sorry. Okay, and that's right there. I think you can get a single mark just for saying that. So again, just make sure you answer every question, because there's always a freebie or two in the question. So we want to calculate the net force acting on the JWST at the L2 point. So at the L2 point, there's going to be two forces that are going to be acting on the point, which we might want to consider. Obviously, in the real case, there might be much more of other celestial bodies around, but in terms of what we have here, we have the Sun and the Earth in a direct line, and we know there's going to be a gravitational attraction force of the Earth to the telescope and the Sun to the telescope that are acting in the same direction. So there's going to be some F attraction to the Earth here. So F. Why is my pen not working? Okay. Sorry. A little bit technical difficulties here, but we'll get past it. Okay. Just some F Earth. Oh, come on. Apologies. Let me see if I can fix this thing. Okay. It's not cooperating today, is it? So F Earth, and there's going to be another force here, which is F Sun. And both of them are attractive forces in the same direction, and they're in the same direction because the Earth, Sun, and the telescope are in one single line, so they're indeed in the same direction. So the F net is simply the sum. That's going to be the F due to the Sun plus F due to the Earth. So that's equal to GMM over R squared. And we want to find the sum. So in this case, it will just be the sum of those two. So in this case, it will be F equals to 6.67 times 10 to the power negative 11 times of the mass of the telescope, 6.16 times 10 to the 3, times the mass of the Sun, which is 1.99, 10 to the 30, all over the radius squared, which is 1.5 times 10 to the power 11 plus 1.5 times 10 to the power 9 squared. And we're going to add that to the F Earth, which will be a very similar expression. Hopefully, I don't have to write that one out. It's pretty straightforward. It's exactly the same, except the mass of the Sun will be the mass of the Earth, and then it will be a distance of 1.5 times 10 to the 9 rather than 1.5 times 10 to the power 11 plus 1.5 times 10 to the 9. And this will give a sum of 36.7 newtons. And that's a single question there. An approximation for two bodies in orbit around each other is the period of the orbit can be determined using the relationship t squared equals to 4 pi squared times r cubed over gm1, where r is the distance between the center of masses of the two objects and m1 is the mass of the more massive body. One assumption of the relationship is that m1 is much greater than m2. Explain why it is necessary to assume that m1 is much greater than m2 to derive this relationship. Okay, that's very important because we know that for two celestial bodies, they will orbit around the center of mass. So there will be some center of mass of m1 and m2, and then they will be orbiting around the center of mass. If m1 is much greater than m2, then the center of mass will be much closer to m1 than m2. And in fact, the center of mass is so close to m1 that basically we are assuming that m1 doesn't move at all. And if m1 doesn't move at all, we are assuming that the radius of the circular orbit is equal to the distance between m1 and m2, and it's equal to that gravitational attraction force. So that's very important. So the main assumption here is just that m1 is relatively not moving. So the assumption is that the movement of m1 is so small that it can be considered negligible, and therefore it's only m2 orbiting around m1 at a constant distance of r away from m1, which is equal to both the gravitational attraction force between the bodies and the radius of the circular orbit. So main assumption is that the m1 stays in the same position. That's the assumption. So that the gravitational attraction force and it's exactly equal to the centripetal force required for circular motion. Motion, so the gravitational attraction is exactly equal to the centripetal force, and to maintain circular motion, so basically the distance of the radius of circular motion, so our attraction distance is equal to r of circular motion. And that is 1 mark, I believe. Let me check that. Yeah, that's another 1 mark here. State another key assumption of the relationship. Another very key assumption is that the circular motion is indeed circular. Okay, that's a very big assumption, because in some orbits it might be an elliptical orbit, and in that case we cannot use the relationship of Fc equals to Fg because the orbit itself is not circular. So assuming that Fc assumes circular motion, so we are assuming that the motion we're assuming that the orbit is circular. It's basically like not elliptical, for example. And you can get another mark for this question here. Question C. In the case that m1 is not much larger than m2, show that the period of orbit given by the relationship stated there, and other assumptions made for the relationship on page 12 are still valid. Okay. So for this question, we'll have m1 and m2. So we'll have m1, we'll have m2. So the center of mass will be like somewhere, like not negligible distance away from m1. So it'll be somewhere, we'll say somewhere there. So therefore, m2 is gonna be orbiting around the center of mass, and m1 will also be orbiting around the center of mass. So in this case, we're gonna find an expression for the gravitational attraction between the objects, which is still exactly the same, which is a distance between m1 and m2, and it will be given by Fg equals to gmm over r. So Fg over r squared, sorry. So Fg equals to gmm over r squared. And this will be equal to g m1 m2 over r squared. And we want to find where is this XCOM, where is the center of mass, and then it's going to be a circular motion around the center of mass. Okay, so center of mass is given by XCOM is going to be equal to, we'll put our reference point to be some distance away from m2. You can also do it for m1. It's going to be exactly the same answer. It doesn't matter. But for just like a random choice, we're just going to choose m2 to be our reference point here. So m2 is the reference point. This will be 0 times of m2 plus of r. This is capital R. Sorry, this is here. It's capital R. So plus r times of m1 over m1 plus m2. This is equal to r m1 over m1 plus m2. So basically, Fc is equal to mv squared over r, so mv squared over r. However, this r here is actually this distance here. So this distance is the circular motion that m2 is actually orbiting around. So m2 does not orbit around m1 in this case. So if that is the case, we're assuming m1 is much bigger than m2. So we're going to be going back to the equation we saw in part B. However, in this case, the center of mass is not a negligible distance away from m1, so rather m2 is orbiting around this x center of mass here. So m2 orbits around the center of mass, which is going to be exactly x com distance away from the center of mass of m2. So this will be some x com distance away, and this r will be equal to that x com distance, not the distance between the two bodies. So Fc equals to mv squared over r. So Fc is going to be equal to mv is going to be equal to, in this case, sum m2 times of v squared over x com. mv squared over com. So now we want to equate fg equals to fc. So in this case, fg equals to fc. So fg, so g m1 m2 over r squared is equal to m2 v squared over x com. So that will cancel each other out. And okay, so m2 and m2 cancel each other out. So now we want to substitute v squared. So v is going to be equal to 2 pi times r over t. So that's the total circumference of the orbit. That's the total distance, is 2 pi r. And the t is the period or the amount of time it takes for a full orbit. And therefore, this is just basically distance over time. So v equals to d over t. So 2 pi r over t is equal to the velocity. So v squared equals to 4 pi squared r squared over t. So we can put that into the equation. So we have, if we multiply both sides by x com, we'll get g m1 x com over r squared. That is equal to v squared, which is equal to 4 pi squared r squared. And this r, remember, it's also referring to the distance between m2 and the distance center of mass. So this will be x com squared all over t squared. Sorry, t squared. So x com will cancel each other out. And cool. I think if there's any simple mistakes I've made, I don't think so. Okay, looking good. So therefore, if we rearrange this equation, we'll have t squared, or rather we have we have t squared equals to 4 pi squared x com divided by g times of m1 and then multiplied by r squared. Okay. So that will be t squared, and then we want to substitute x com back for the expression we derived here. So rm1 over m1 plus m2. So t squared equals to 4 pi squared over g m1 multiplied by rm1 over m1 plus m2 times r squared. m1 and m1 will cancel each other out. And now we have t squared equals to 4 pi squared. R times r squared is r cubed over g times of m1 plus m2. And look at that. That's exactly what was required for the question. Correct derivation there. And this will be a 2-mark question if you can get the derivation correct. Question D. The phases of the moon are caused by relative positions of the Earth, Sun, and Moon. A full moon occurs when the Earth, Sun, and Moon are directly aligned. The Moon takes 27.3 days to complete one 360 orbit around the Earth. However, because the Moon must orbit more than 360 to return to a direct alignment with the Sun and Earth, the time between one full moon and the next is more than 27.3 days. Okay, so this question might look very confusing and challenging when we first look at it, but really it's not really that difficult once you actually drill down to the nitty-gritty. So we know that the Earth is going to be rotating around the Sun at some angular velocity, and the Moon is going to be revolving around the Earth at also some angular velocity. And we know that after a full moon, the moon must at least revolve around the Earth one full circle around the Earth before it returns to its original position. However, in this time, in that whatever time, let's just call it in that big T time, the Earth would have also moved some angle away from the sun, which we'll call this as some theta away from the sun. And therefore the moon has to travel this theta more distance in order to be aligned from the moon. And then only after it travels this some theta, it will be realigned with the sun. So it's actually, in order to set up this equation, we know that we'll just call the time it takes between two full moons to be t. So let t be the time between two full moons. And we know that the amount of revolutions traveled would just be the period divided by the number of days. In this case, t divided by 27.3. So that's the total number of time between two full moons divided by 27.3. This will give us the expression of the number of revolutions the moon has traveled around the Earth. So this is number of revolutions the moon traveled. And we also have t over 365.25. So this will be the amount of theta time that it would have taken for the Earth to move some theta in that time it took between the two full moons. So this is the let's just say the angle Earth in that time. Okay, so basically we can just say that t over 27.3. So this distance traveled is going to be equal to 360, so a full revolution plus whatever angle that the Earth traveled in that time. So this will be equal to t over 365.25. This will be equal to t over 365.25 added to a full revolution, because the full moon has to travel one full revolution, and then also added to this some angle the Earth also traveled in that time in order to be realigned with the Earth and the sun in one straight line. So this will be t over 365.25 plus 2 pi. So 2 pi if we're working with radians. You can also use degrees, it doesn't matter. So 2 pi. So be t plus of 2 pi. And now really it's just a matter of rearrange to find t. So we have, just get a calculator, don't mind me, give me a moment. So sorry, just give me a quick moment. My thing is not. Okay, so obviously I think I've done something wrong here. So just give me a moment. So t equals time between two full moons. Okay, yes, of course. Okay, so the very, very easy mistake, and I apologize. Okay, so what we have here, when we have t over 227.3 and t over 365.25, this is actually the number of revolutions made. Okay, I've already stated here, this is the number of revolutions made, and this is actually I should actually be a bit more careful with my wording here. So this is actually the revolutions the Earth has traveled in that time. So these are all in terms of revolutions. So if we wanted to convert it to the number of radians, we have to multiply both of them by 2 pi. So it'll be 2 pi t over 27.3 minus 2 pi t over 25.25 equals to 2 pi. So that should give us the right answer. So if we have we had. Yeah, and that will give us an answer of t equals to 29.5. So apologies for that. It's a very simple mistake there, but so that's 29.5 days. So that's what we expect for the answer to be. Yes, just be careful because we've already defined t as a time between two full moons. So t over 27.3, that's not the number of radians traveled. That's rather the number of revolutions that the moon has traveled. So we need to convert that to the number of radians first. So we multiply it by 2 pi first. So that's a very crucial there. So, but we should get the answer of t equals to 29.5 days. And that's the answer. In terms of marking, how many marks for this question? I'll have a look. This is a 2-mark question. 2 marks for this question here. All right, and that's it for this this paper. If you have any questions, if anything didn't make sense, please feel free to leave it in the comments down below. I hope you enjoyed the video, and I hope to see you all in the next one.